Welcome to Math with EJD. We're still talking about inverse Laplace transform. And we've been considering methods for inverse Laplace starting from the last video. So there we saw partial fraction decomposition. When you have a rational function, and then you have to decompose into partial fractions. Partial fraction decomposition. In this video, we're considering the convolution theorem. Convolution theorem. Afterwards, we'll be considering an idea in complex analysis, which is called the residue theorem. All are methods for looking for inverse Laplace. So, like I said already, our consideration. Oh, okay, this is already done. So we're going for convolution theorem. So convolution theorem. So the convolution theorem is a powerful tool for computing the inverse Laplace, the inverse Laplace transform of product, a product of two functions. Specifically, if you have f of s, so the normal f of s in the frequency domain is a product of a g of s and an h of s, right? That's where we use the convolution method. So if that happens, right, specifically if we have this, then the inverse Laplace transform, the inverse Laplace transform of f of s is given by the convolution of the inverse Laplace transforms of g of s and h of s. And that is this. You have f of t equals g convoluted with h of t, and that is integral from 0 to t of g of t minus tau, h of tau d tau. Okay, we have that expression. So given this, we have this in the time domain. Okay, so this theorem is particularly useful, is particularly useful when dealing with complex products. It's complex products where each factor has a known inverse, Laplace transform. An example would be this. Given f of s equals 1 over s plus 1 multiplied by 1 over s plus 2, find the inverse Laplace transform. And the inverse Laplace transform So um, the first thing we want to do is identify the factors. Identify the factors. So in this case, g of s is 1 over s plus 1. H of s is 1 over s plus 2. So that done, we move to the next thing, which is to find the inverse Laplace transforms, the inverse Laplace transforms of g of s and h of s. Well, maybe from memory or from standard tables. From memory or from standard tables. Um, so we already know that the inverse Laplace of g of s is the same as inverse Laplace of 1 over s plus 1, and that is simply e raised to power minus t. I think we saw that much. I mean, we know that's a very common one. On the other hand, the inverse Laplace transform of h of s is the same as the inverse Laplace transform of 1 over s plus 2, and that is easily e raised to power minus 2t. Now, with this in place now, we can then go ahead and use the convolution theorem, step 3. So use the convolution theorem, use the convolution theorem to find the inverse of the product. Okay, so that means that f of t now is integral from 0 to t of e raised power. Don't forget the formula again. This is it right here. So that's g. We have g. Okay, I guess I should even write that, right? So let me write it as so we can follow it slowly. So f of t is integral from 0 to t of g t minus tau, then h of tau d tau. So we already have, of course, this is our g of t now, and this is our h of t at the end of the day, right? Okay, I think it's better to write it here. So this is g of t, and this is h of t. Okay, so we have integral. So we have small f of t is equal to integral from 0 to t of g of t minus tau. So that's e raised per minus t, right? So instead of minus t, we just have t minus tau. So that's t minus tau. Then h of t is e raised per minus 2. That's e raised per minus 2 tau d tau. So we need to deal with this now. Thankfully, um, okay, it is in the tau domain now. So any t you see here is actually going to be like a constant. So we have f of t here to be integral from 0 to t e raised per minus tau times e raised per minus t times e raised per tau. If you open that up, then times e raised per minus 2 tau d tau. Okay, so e raised per minus t here can be taken away. You can take that out. You can factor it out. So f of t now is e raised per minus t out here, integral from uh e raised to power t minus tau. Okay, this is t minus 2, I mean tau minus 2 tau d tau. Okay, that's what we have left. So that means that f of t is e raised per minus t, integral from 0 to t, e raised per minus tau d tau from 0 to t. Okay, so f of t now is equal to e raised per minus t times, when you integrate e raised per minus tau, that's simply e raised per minus tau divided by minus 1. Because if you differentiate minus tau with respect to tau, that's minus 1. And that is from 0 to t. That's when from tau equals 0 to t, right? So now f of t, okay, I think at this point I want to switch back to green. So f of t is equal to e raised power minus t times, now because of this minus now, um, we can even take the minus outside, right? So we have uh minus outside into e raised power minus tau from 0 to t. So 0 to t, these are the limits for tau. So f of t is e raised power minus t times minus. When you put t, you have e raised power minus t minus. When you put 0, you have e raised power minus 0. Okay, so this is f of t equals e raised power minus t times minus e raised power minus t minus 1. Okay. All right, because of the negative sign, so you can put the negative sign back inside. So you have e raised power minus t into 1 minus e raised power minus t. So yeah, we have this now. Um so this is e raised power minus t, e raised power minus t equals 1 minus e raised power minus t. Okay. Um, yeah, is there anything else to do with this? Yeah, I think that's about all of it. I think we have got the results. So if we take the tau inside, right? If we take we can take the t inside if you like. So that's f of t equals e raised power minus t minus e raised power minus 2t. So basically, we just say we can just say thus the the inverse Laplace transform. So I think it's exactly what we did before for partial decomposition. So that's the inverse Laplace transform of f of s equals 1 over s plus 1 times 1 over s plus 2 is f of t equals e raised power minus t minus e raised power minus 2t. And that is how that goes. Yep, so that's it. Before we go, let's take practice questions. So you can practice with this. Um, use the convolution theorem to find the inverse Laplace transform of 1 f of s equals 1 over s plus 1 times, okay, let me just move now. 1 over s plus 2 times 1 over s plus 3. Okay, I mean, let me just make it only one, right? Let me make it only one. Of f of s equals 1 over s plus 2 into s plus 3. You can easily split this up, you know, it's just the same thing as 1 over s plus 2 times 1 over s plus 3, basically. So you can do that. So let me see your answer in the comment section, either on Facebook or on YouTube. Okay. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then if you have subscribed to this channel, thank you. If you haven't, please go ahead and do that. And don't forget, everybody, to hit the notification bell so you can always get alerted each time a new video is released, because there's a lot here already to learn and there's a lot more coming. I don't want to miss any of this, right? Then of course, like and share so that more people can have access to this great content. So like, come your way again. Keep doing maths right. In the next video, we'll be talking about the convolution theorem, which is a concept in complex analysis. Bye.